We're going to start with a quick agenda, so we'll review, again, some of the challenges with comparative analysis. And just as an introduction, I know, Scott, you and I have been talking about this, but it seems that comparative analysis is becoming much more prevalent in what people are doing when people are doing simulation, more so than maybe 5 years ago.
Oh yeah, I think that the advances in computer power has really led to an increase in the amount of simulation that people are doing, and simulation is actually becoming a greater part of the design process, and so you get this balance now of simulation and experimental data that people are trying to analyze. So comparative analysis is a natural thing that's going to happen in that case.
And then it certainly leads to a number of challenges, which we'll talk about. We're actually going to walk through in detail comparing test and simulation data. In this case, we're going to use simple data because we want to get into enough detail so that everyone has an opportunity to see how you might do this with, say, test data that you may have laying around that you want to compare with either your CFD or other simulation. The other thing we're going to do is take a look at what happens when you're looking at different configurations when looking at simulation and how you compare that as well. So let's go ahead and review then a couple of things. And I want to put this in context, and perhaps one of the things that I hear most often when we start thinking about comparative analysis is, as John Moffat pointed out, physics is imagination in a straitjacket. Or as Fisher said, the great men of science are supreme artists, because it's that how do we get from the physics to the art of trying to compare it in a meaningful way?
Sure, it's all about your perception and really being able to see what's happening in your data.
Yeah, so it's really how does one see what's going on? Yeah. So to just review, there's a couple of things we talked about as challenges, and data registration was one of the core things, comparing apples to apples.
Right. One obvious thing is that you really need to get consistent data. If you have different units, you obviously can't compare it. So you need to do some sort of manipulation to get your units consistent and scale your axes properly. And you have to register it. Oftentimes you have different coordinate systems. In particular, experimental data, wind tunnel data, for instance, you may have your data in wind coordinates, which is related to, aligned with the relative wind, whereas simulations frequently, the data is in some sort of body fixed coordinate system. Mm-hmm. So you need to do some rotations and perhaps some translations to get consistent coordinates.
Mm-hmm. And in addition to coordinate systems, the integrated quantities are certainly an issue that you have to be aware of.
It may not be obvious with integrated quantities that they are in different coordinate systems. If you have a force coefficient, a lift coefficient, or a drag coefficient, you may find that they're totally off and not know why, and it may be that you're using slightly different coordinate systems for your integrations.
And this has come up quite a bit. I know that there's several groups in NASA that are trying to validate, people who want to launch in NASA facilities are trying to validate the data they bring to the table. Oftentimes they're using different coordinate systems, and being able to evaluate the two solutions to make sure that they're consistent, well, you have to figure out, make sure that they're in the right coordinate system. Again, this is mostly around the derived quantities. So in terms of analytical comparisons or deltas, we talked about this a little bit. This is one of the challenges we have, is finding those minute differences. The fine structure, so to speak, can be a real challenge. I think this is good. I was just saying, this is a pretty good example where, this is the classic C. For those of you who have young kids, if you've ever looked at the Highlights magazine where they have what's different in these pictures, well, that's what we're doing as scientists and engineers now. It's really what are the differences, and boy, I tell you, if it wasn't for those blue circles, I'm not sure I would see the differences in these two models myself. The other thing we have to be consistent on is looking at deltas between the grids, and when we walk through our example, we'll actually show you how that can be something you really need to pay attention to.
Right. It's so much easier if you have the same grid in the, that you're working with, or the same locations for your data. Um, Frequently, that's not the case. If it's not the case, then you need to do some sort of interpolation, and so that you can actually compare oranges to oranges. And I mean, it's the same as the coordinate issue. You need to be at the same, comparing the same the data at the same location, so you can get useful information.
And probably the most common type of visual comparison is just that. It is a visual comparison where you look at perhaps two sets of data or two different configurations in one environment. So one of the things we'll do in our second example is show you some strategies on how you can take advantage of the fact that you can look at different configurations and really try to set up a simple way to look at it. And one of the things that I think is really kind of fascinating, there's a group at NASA Ames that's looking at configurational analysis, and they're looking at making small perturbations to, say, angle of attack, and they're using their visualization wall, and they're looking at, say, 1,000, in this case it would be 1,000 configurations up on the screen, or I guess it's a couple hundred, it doesn't matter. But the fact is they can look at each one of those configurations, and the eye can very quickly see how those variations in angle of attack impact the flow. So it's another way to do that comparison.
Yeah, it's a good way to do the comparison. Now, you may not see the minute differences quite as well, back to the tiger picture, but certainly you can see the larger scale changes extremely well. The eye is good at detecting the difference between images, the difference in certainly in position between images very well. It's maybe a little less good at detecting the difference in color between images, but still it can be done.
Yeah, so what I'd like to do at this point is really, again, paint that picture. Why is this so important? Why does this come up so often? And that has to do with we are working in a very heterogeneous environment. Regardless of where you go, if you're working on airplane design, or it could be automobile design, it could be engine design, you're likely going to be working in a very heterogeneous environment where you're looking at structural analysis, test analysis. Of course, CFD is playing a larger and larger role in how people are designing things. And now there are whole groups who do kind of multidisciplinary optimization. And so this is really the crux of why comparative analysis is so important and what we'll be talking about in our example. So in the first webinar in this series, we talked quite high-level theoretical on how one can take a look at data from, say, test and from simulation, and to do kind of a quantitative differencing. One of the key pieces of feedback that we got from the audience was, well, we'd like to see how you actually do that. So go a little bit beyond the theoretical to the practical. And so what we're going to do now is we're going to dive into an example, and we're going to spend some time showing you how one can generate these type of plots. And hopefully along the way, we're going to discuss some of the challenges you have with looking at data like this. So in this, let's go ahead and jump out here, and I will go ahead and bring open the data that we're going to use. Now, these test data are here, and I'll go ahead and open it. It turns out we're going to start from Excel, and I suspect for a lot of people this is not uncommon, that data is often collected in Excel just because it has a kind of a convenient mechanism to put data in.
Oh, sure. Yeah, I mean, you need a place to store your data and do simple analysis with it, and Excel is sort of the default for most people.
Now, and Excel's a pretty powerful tool. You can do a lot with it, and boy, from my travels and talking to engineers, it's amazing how many people have figured out how to work around limitations in Excel to do some pretty sophisticated analysis. But there are some real limitations in the way that it likes to plot data, and so it may not be a perfect solution, especially when you're talking about deltas and you're looking at data that's very different. So in this example, which we discussed the previous webinar, you can see that although there's some parity, we have, say, data starting at 650 RPM, whereas we have data here starting at 700. Now, the data from the simulation is much more regular, and there's certainly a lot more of it. And so if I go all the way down here, you can see that there's significantly more data coming from this numerical model than there are from the actual test. And we're looking at two different potential simulations. So here's one that actually started at much lower RPM. Now the good news is, if we want to just bring this into a tool that's a little more powerful, we'll bring this into Tecplot, which is not a big deal. It's pretty easy to bring over. We have an add-in in Excel, and we'll bring the data directly, and it doesn't really matter how it opens. So one of the key things we want to look at is, well, what are we actually looking at in terms of data? So we're going to first look at each one of these lines as an XY plot.
Right. Yeah, that's where you get the most quantitative information is from the XY plot. Of course, you're limited in scope to just the region that you're plotting.
So in this case, if we wanted to look at for each one of the zones, and in this case the zone's just each RPM value, and we're going to look at, for all the zones, we're not going to look at pump RPM because that's not all that interesting, but if we wanted to look, say, at average pressure versus torque, for example, we can create all of those line plots in just one click here. And now what you're looking at, that's the performance space. So each one of these lines represents an RPM value from, I believe, 600 to 2500. Now, we didn't actually label what the individual RPMs were. Of course, we could do that. But this is probably the best first way to look at the information. So we'll move this over here. Now, we want to extend our analysis because we are interested in differencing, but we want a difference based on the performance space. So instead of just looking at, say, a series of simple line plots, we're going to take advantage of the fact that we can work in this frame environment, and we're going to look at, say, a 2D representation of these data. So the data themselves, again, there's a fair number of zones. And what I'm going to do very quickly is go into the axes here, and I'm going to just make them independent because we want them to basically fill the available space. If I fit this and turn on the mesh, you can see that here are the different RPM values. Now, ultimately, probably the easiest and most effective way to evaluate these data would be to do a simple triangulation. So if we just triangulate the data now to make a mesh for all the data that we have available, now we can kind of look at this more in the way you would look at a computational mesh.
Right, the triangulation, what it does is it allows you to actually look at the variation between the points. And so within Tecplot and I'm sure most plotting applications, you need to have some sort of a underlying grid structure in order to really represent the variation between points. And this is a very convenient and quick way to do that.
So if we want to extend then the analysis, one of the key things, when you look at test data, sometimes you have some values that don't make a lot of sense. Like you can have an area where the torque is 200,000. We know that, frankly, that would be a pretty high torque on an engine. It might explode, I'm guessing.
Yeah.
So we know that that's just the nature of experiments. Sometimes you are going to get some values that don't make a lot of sense. And so you may, in fact, want to remove values interactively because we don't really care about values that high because they're just not real. But we do, however, want to evaluate these levels, and so we can kind of pick the torque values that make the most sense for us. So if we just decide we're going to go to a new set of levels, and we'll go from torque values of, say, 100 to, say, maybe 2,500, and we'll look at, say, got a mistype here. There we go, 2,500, and we'll look at about 20 levels in that range. So one of the things you can see right away is that there is some fine structure that's in the higher average pressure values that we need to probably refine. So we'll add a couple of contour levels here just to make sure that we understand what's happening out here in the higher average pressures. So if we then take this and we talk about how does one quantify these results, there's two things going on here. Here's the simple XY line plot. Now this is the performance space that these line plots represent. But if we want to interpolate values, and this goes into, well, what if we don't have data at, say, 1,100 RPM, and we want it? And so one of the key things that we can do, based on this data, is we can create, now that we have this performance space, we can create lines that we can use to create additional XY plots for the data above. So in this case, we're going to specify, or we're going to do some contouring, line contouring in this case. So we'll set up our second contour as just the pump RPM. And you can see here are the values we have. Now we're going to reset that to give us 50 values. And that's not all that important, but when we now evaluate that contour, not as just a simple flooded contour, but we want to now understand those lines. So we'll do lines at pump RPM. And we'll do lines at flood. And it should be pretty messy. You can see here are the values that we're looking at on pump RPM. But those data now are extractable. So if I extract those contour lines and I generate yet another frame, so we have now 3 frames. This frame I can actually do a very similar thing where I'm going to make an XY line plot, but now instead of looking at the zones that originally came with the data, we can look at any of the contour lines for, say, an RPM value of 3,900, even though we don't have real data there. So if we look at average pressure versus torque, and I'll close this quickly. So there's my average pressure versus torque at that value of 3,000. So we can really extend how we look and target these data. So this is kind of, again, a convenient way to quantify, but we haven't really talked about the differencing component. We've really only spent time at this point talking about how you might analyze a set of data.
Yeah, that's true, and there are other ways of doing this extraction. Tecplot is very powerful in that you can extract the contour lines. You can extract. You can actually specify the line or click on points. This, in this case, is certainly the best way to get the most data out quickly.
And one of the other things we can do that's kind of convenient is really try to make this all in the context of perhaps the experimental apparatus. So if we had a picture or we had some way we could actually make this into a report. In the interest of time, we're actually going to pop into the second data set, and we're going to go ahead now and go back to Excel. And instead of looking at that original set of data, which was test, let's go ahead and evaluate the data from the numerical model. And using the same methodology, we can bring that, oops, grab all this data here. Okay. And we'll pop it into Tecplot. And again, the same kind of analysis is available to us. In this case, we'll just go ahead and start right in 2D. We'll go to the triangulate, and we'll triangulate all these data together. Same thing we just did. And the last thing we'll do is we're just going to write this data out. So we'll write out just our triangulation. And I'll put this on the desktop. And I guess it doesn't really matter what we call it. So
now the reason, of course, you're writing this out is that when you use the Excel add-in, it actually launches a second Tecplot. And so this is, you need a way to transfer it to your original instance of Tecplot so that you can compare them.
Right. So let's go ahead then, and we're going to now bring in the data, and we want to compare it with this data. So one of the things I'm going to do is I'm going to almost copy and paste this, and I'll move it over. So now we have 2. We know that look and feel information is the same. The only thing I'm going to do different now is I'm going to load a data file. And the data file I'm going to load is in Tecplot format. And we're going to add it to our current data set. And the only thing is we're going to grab the data I just wrote out, which should be down here as text file. Okay? So you can see it automatically brought it up. I want to only look at that particular value or that particular zone, so I will just show that one here. Let's see here. Just like that one. Okay. So here we are. Let's go back. So this represents the test data, and this represents the, or I'm sorry, this is the test data, and this is the simulation. You can see that they're using the same contour values. It's because I copied and pasted from the first data to the set, this first frame to the second, so it retained all the style information. That's just want to make sure that I turn off.
Yeah, I think you still have the others on.
Let's go back over here. Actually, this is the one we want to deactivate.
Mm-hmm.
All right. So you can see that we already have a simple way. We don't really need these lines any longer. So let's just make sure that we look at flood to flood. And let's take advantage of something called frame linking. Again, when you're doing visual comparison, the ability to link the contour levels is critical. Because now if I go in and I want to refine an area of interest from the simulation, you can see that it updates both plots simultaneously. Now the last thing perhaps we want to take a look at in terms of linking would just be the overall view. Again, if you zoom in and out, you'd like to be able to zoom in and out simultaneously. So we'll actually make sure that the X range and the Y range are the same. So if we zoom in and out, you can see that we actually are looking at the same space. And that includes the XY plots above. Okay, there was a good question that came in from Molio and says, how do you extract a set of data from a rake location? For example, your example does not show controlled locations of extracting these data. We do have an application which is called a precise line extractor, which allows you to do that. So you can actually set the start and finish points and how many points you want to extract. We also have a tool that allows you to kind of interactively do the same thing. So if I wanted to extract data this way, I could.
Right.
So how are you able to add contour lines using the mouse? There is an option in Tecplot where we have add contour levels. If you select that mouse functionality, then you can just come in and add them interactively. Of course, you could also do that the old-fashioned way, which is you could add a level. Let's say if I wanted it 340, I can add that level as well. Okay, now what you showed. Okay, oh, let's try to answer that as we go along here. So let me put these data back. Okay, so this is probably the first part of it. Now we want to talk about how does one quantify this. And this is where I want to spend a couple of seconds on triangulation versus interpolation.
Sure. The triangulation is actually gives you the true data at the points, whatever the data that you read in is, and then varies it between the points. Interpolation may or may not do that. But the interpolation allows you to actually do cases where it would be difficult to triangulate. Perhaps you want to go to a subset of the full domain, or even extrapolate out beyond the end of the domain. There's a lot of things our interpolation capability allows you to do that you can't do. There's a lot of cases you can't triangulate that you can interpolate.
Now, the other thing that comes up with some frequency, there's the difference between doing kind of a linear interpolation, between doing that, say, and doing kriging. Where are the areas where using kriging might be more effective?
Sure. Kriging is an interpolation technique that came out of geostatistics originally, and it actually is pretty effective at, well, one thing it does is it gets you, it goes through the actual data points when you're at the data point. And it also gives you pretty good variation between them in terms of a reasonable expectation of the variation. Now, one thing you mentioned, the linear. Well, triangulation always does linear between the points, and that just if you only have a few points, that may not be a very interesting way to look at your data when you know that it's not linear between the points. It's just that you don't have that many experimental points. So kriging actually is a statistical technique that works well. It minimizes error in a certain sense in the interpolation, and so it's quite useful.
So in this context, what I've done is I've actually created two data sets which are identical, and we're going to use those for differencing. And we're going to take advantage of one of the interpolation methods. So in this case, it may be just as easy to do a linear interpolation from our triangulation into a rectangular zone, which the first one I created here. And so we're doing that. This is the test data. And then we'll do the second triangulation into a different zone here and compute that as well. So you can see now that the contours have changed. What I'm going to do is we're going to make another frame. Paste that one on. All right. So now we have a frame up here and down. In this particular frame, let's leave it back where it was by deactivating these. And up here at the top, what I want to do is just look at those two new zones which I used the interpolation on. So let's go ahead and just look at those. So we'll look at the first one here. We'll look at the test data. So I'm going to show only that one. And then I'll copy and paste this as well. And now we're going to look at over here, instead of looking at the test data, let's look at that simulation. Again, the intent today was to be a little more rigorous so that you have an opportunity to understand how you might do this with the work that you're doing. Okay, so here are the two. This is, again, the interpolated values from the simulation and from the test. A couple things to point out. You can see that there are areas where, because of the way we did the interpolation and the value starting at 0, where there really aren't any data. And so probably the first thing we want to do is take advantage of the fact that we don't want to see data that is meaningless. So we're going to cut off below a given value, and the value for right here, we'll cut off below, say 0 or 1, something that will get rid of all the low values which are meaningless here. Okay. So now you don't see it. If we turn on the mesh, you can see there's still mesh out here, but really there's no data. Similarly, if you do the same on this side, there's no data. Okay, so finally, what we want to do then with this is look at the actual quantitative difference. So to do the quantitative difference, we'll create a new frame that we'll put into 2D. And let's just look at one of these zones for not important. Which one? And the last thing, of course, we had talked about this earlier. Because these data aren't rigorously they're not necessarily something that you need to look at in a 1-to-1 ratio because it's not something physical. We're looking at just a different data space. So we'll look at an independent just so we can maximize the viewing area. And the last thing we're going to do is just create that delta. So we'll create a delta function, and we'll make this a new function.
In our data alter, you need to put names in those curly brackets.
So now we have a variable that is delta. And what we want to do is just on one of these now, we want to say, okay, well, we want to look at that delta from the first zone, which is actually this rectangular zone here. We're going to actually look at delta from zone 82. So we'll look at V3, which is the value we're interested in, for the zone, which in this case it happens to be 81. And we're going to minus that from V3 from zone 82.
I think you have a number.
And now if I turn on the contour and look at delta, you can see the delta map between the two.
Mm-hmm. Now, once again, we have some spurious data in those regions where the two domains, the experimental domain and the computational domain, don't overlap.
Right.
And so you can use the same techniques you used before to sort of cut out those regions.
So if we want to look at deltas that are more meaningful, say from minus 1,000 to a maximum of 300, we can do that. And now you're getting a different map. And similarly, if we just go through and say, well, where are the areas where we are seeing the most variation between the numerical model and the test data? And we can kind of quickly look at that heat map to get a sense. Of course, we could quantify this as well by looking at an XY line plot. So if we then just clean this up, so to speak, if I were to take all this and look at it in the layout, which I've already done, I'll just open up that layout so you can get a sense of what you might create at the end. Let's look at the test and simulation compare. Okay, so here's just yet another heat map. Similar thing. We're looking at the test data, and we're also looking at the deltas between them. So you may want to compare the data this way, or another way that you can look at that would be a little more quantitative, where you have your test data, and you also, down here, you have test, simulation, and then we look at the actual delta, and this is just taking those lines and perhaps looking at a little cleanup. So this is kind of a mechanism that you can present this information. Again, typically I would take this data directly into whatever your reporting mechanism is, which, based on my travels, is becoming more and more often PowerPoint.
Yeah.
So that's maybe good, maybe bad. And we'll go ahead and pop that onto the clipboard, and if we walk into PowerPoint now, and my PowerPoint slides are actually over here, we can jump in, we'll make a new slide, and we'll just go ahead and dump in the data, and voila, we can kind of go with it. Here's the difference. And we can present that and be off and running. Okay. So that represents what you do when you're trying to do more analytical comparisons. One of the key things to point out here is that when you're looking at maybe more CFD data, and perhaps you're looking at pressure on an inlet, and you're trying to interpolate values from, say, onto a fine computational mesh, you really have to make sure that you use the right interpolation methodologies, because you may, in fact, run into some artifacts.
Yeah, that's true. And the other thing is you have to be very aware of any sort of stretching within the grid, because a lot of these interpolation techniques that we have actually are sort of a uniform spacing along the line, and sometimes you have very fine spacing near the wall. Now, the one you did with the contours actually will vary the spacing according to the underlying grid structure. So that's a good way to go if you're trying to if you want to retain the spacing that's in the underlying grid structure.
Now, there's a question about doing kriging on 3D surfaces, and so could we do this for, say, delta, lower and upper pressure on a wing?
The answer is no. It's the well. Let me be careful here. You can do kriging in 3D, but it's difficult to avoid it actually going from the upper surface to the lower, and using a value on the lower surface. To do that, you would probably need to define a new coordinate system that unwrapped the wing, the surfaces of the wing, and then do your kriging in 2 dimensions in the new coordinate system that, say, runs from the trailing edge around the leading edge back to the trailing edge, and then you would be able to do kriging. But that's extra work.
Okay, so let's move into perhaps a second type of comparison, looking more visual comparative analysis, strategies for looking at multiple configurations, which is, again, an area that I'm running into quite a bit when I talk to customers. And people are looking at multiple configurations of CFD runs. I don't know if you want to make a comment on that, Scott. Is that consistent with what you're running into?
Well, that's sort of a standard thing, of course. When you're looking at design, for instance, you want to vary configurations so you can understand how things work. Performance, even just looking at the, say, if you're looking at an airplane, of course, the configuration changes in different regimes of flight. So they're going to be changing the configuration, say, extending the flaps or the slats. And so sure that's going to happen, and you need to be able to do some comparisons in those cases as well.
Right, and that would be consistent again with what NASA's doing when they're doing changes in Mach or angle of attack. So let's take a look at an example that is perhaps a little less interesting, but perhaps illustrates how one can take this approach. So let's get out of PowerPoint, or try to. See if Microsoft allows us out.
Okay.
There you go. And we'll close a couple of these things. They're not important for this moment. So let's go ahead and go back in, and we're going to bring in a model and we're going to take a look at a couple configurations for a problem that a particular building manufacturer was having, that they had an exhaust vent, and they were getting re-ingestion of exhaust fumes back into the HVAC system, and that was a big issue. They want to understand what was going on, and so they used CFD and prevailing winds, looking at different times of the year and the prevailing winds during those times of year to understand why are they getting this re-ingestment or re-ingesting phenomenon. So the data themselves are actually in Fluent. It's not all that important, but we'll go ahead and just grab a base case here, which I put out here, and let's just look at the first base case here. And for convenience, I'll go ahead and average these to the note. It's not all that important, but it will be more important when we're doing delta. So let's go ahead and load these data in. So we'll do what most people do in their cursory analysis of a CFD result, is just a simple exploration of the flow domain or the flow physics using a slice, for example. And I'm going to turn off translucency since this is not necessary. So again, we're going to just move in here and take a look at the area between the two buildings. So you can see that there's an area of high pressure where the prevailing winds are coming this way. There's a lower pressure area here, and what they want to understand is, I zoom in a tad, you can see there's a small exhaust port, and that exhaust port, although you can't see the delta pressure very much, but of course, that's where it's really great to have the ability to go in and add additional contour levels, because now I can refine that fine structure, and you can see that there actually is some exhaust gases coming out. So they were interested in re-ingestion, so we're going to grab a stream trace and just drop in a series of rakes and see, are they seeing any kind of swirl in between the two buildings. And if I zoom out a tad, I guess you can see that that's in fact the case, that they do have some eddies forming between the two buildings. And you can't perhaps see this very well, but if I zoom in a bit, down towards the bottom of this building, there's actually an inlet in there. So it's perhaps not obvious from the flow domain, but there actually is an inlet. And so they were interested in understanding, why are we under certain circumstances getting this kind of recirculation. So this is one example, but as I pointed out, they actually were looking at a number of configurations. If we want to look at those configurations, we need a simple way to do it. And so we need to understand, well, this is all fine and well for one configuration, but what if I have 10? So I'm going to go through this under the idea that we have, say, 4 or 5 configurations. And let's just start with 4 because it might be easier. And what we'll do is we're going to look at each one, but we want to do it in a convenient way. So we're going to load the data. In this case, we'll start with the first data set. And we're going to take advantage of something called the style file. And Tecplot is not important. Just look and feel information that is not data set specific. And we use that because it makes it a lot easier to evaluate these things. So the data should be right here. So we just called it look 1. And it's really look and feel information. Okay, so there's one view. But again, we have a lot of data sets that we want to evaluate. So if I then bring in another data set, I'll load a second solution. So we'll look at, say, the second case. And the same kind of thing, we're really interested in understanding, we want these things to look identical. So we're going to look at that style file as our mechanism to make sure that we're looking at apples-to-apples comparison.
And the style files are really easy to create if you've never done it. It's in the drop-down that Durrell just did, you saw that there's actually a save style and a load style. And the save style, you just set up the style you want and you save it, and you can use it in other frames.
And same kind of thing here. We have the data available, and the thing that we'll want to be able to do is look at 4 of these. Now, I could have done this all automated, but I chose to walk through this in detail so those of you who are doing this in the real world can see how one does it. Now, this could have been automated completely, but I thought in the interest of more of a tutorial, I would do this. It says, hey, can you use frame linking as well as opposed to styles on each frame?
Certainly, you can use frame linking. We can't link everything, but it's right up there, in the list, and I believe you can link most of what we need to link here. Certainly, view.
The thing about linking, and one of the limitations perhaps in using the linking functionality, is you can't do the linking and stream trace placement.
Right.
So outside of the stream traces, everything else can be linked, the slice position, contour levels, and what have you. And let's load in one additional file. Okay, while we do that.
But it would make sense to link the other things, the location and everything, so that you could rotate one and they would all rotate in the same way, or zoom, or that would be helpful in the evaluation of the data.
Yeah, and we're actually going to link these guys together here in just a second. And again, we'll use our style as well. Can you zoom on show how it frames? Yeah, that's the frame linking, so let's go ahead and turn that on. A couple of people are asking about it. If we just hop in here and apply to all the frames in this group, if I rotate one now, it rotates all of them. So you can see these three solutions look reasonable, and right away you can see this solution doesn't look reasonable. So the question is, oh, perhaps this one's not converged.
Yeah.
So this is a good way to very quickly, without having to do anything, well, this guy doesn't look like it's the right solution, so perhaps let's go ahead and load a different file, and we'll replace the data set that's in there. But we want to look and feel information to stay the same. We're going to remove all these, and we'll add, say, the fourth solution. And I think if you look here, it may be that, in fact, that one wasn't converged. So
that would make sense.
And I know for some of you, you may dump out your convergence, looking at every 100 iterations or what have you. You may not. So let's just make sure we're consistent here. Okay. So very quickly, you can see, again, based on just these configurations, and that looks like that. It needs to be slice position, isosurfaces, contour levels, apply all. So now we can kind of walk through, and you can see, depending if you think of these as the 4 seasons, and if you look at the prevailing winds, you can see that at certain times during the year you perhaps don't have as much ingestion, whereas sometimes during the year you may have quite a bit because it may be more windy. Now, if we wanted to look at the delta of, say, velocity magnitude, of course, if we want to calculate something like velocity magnitude, it wasn't something that I dumped out or that was dumped out in the Fluent solution. So we'll go ahead and just calculate it here real quick, and we'll put it on demand. It's not overly important. And then if I come in here, I'm going to just change the contour to velocity magnitude, which is a new variable I have access to. As soon as I do that, it's going to make that calculation again. Make sure these are consistent. And actually, they're different solutions, so we'll have to go through. But for the sake of argument, let's just look at one solution for this moment. So you can see that the velocity magnitude, there's not a lot of variation between the buildings, but we'll, again, add some contour levels to refine the fine structure. And the last thing we want to do here is we want to create perhaps an animation which we can then use to just show the different seasons. We're going to use keyframe animation. We'll actually use the relative velocities by looking at, say, stream trace animation as well. But let's start with kind of a simple animation. Now, for those of you who've been using Tecplot, we do have something called the Quick Macro Panel. It allows you to do things like load an add-on. And if it happens to be, you can put the text string here and it will actually load it in. The other thing that you can do for those people who work with add-ons is you can, in fact, drag and drop an add-on directly onto Tecplot's work area here, and it will load it. And this particular add-on allows you to tile the frames, and so if I just, say, tile these together, I'll maximize this. You can see I can very quickly just put these into kind of a nice tiled array. And again, remember, they're still all locked together. We want to change the orientation axis rotation, so we'll just hit O. So now we rotate in between the buildings. And we're going to animate these with a keyframe animation here. So we'll just put in a few views that will help us understand what's going on. And if we just animate these all on screen, just make sure this looks like what we want it to do. So you can see these are at the different prevailing conditions. And it looks like it's going to work, so I'm going to stop this because what I want to do is put this into PowerPoint. So I'll dump this out to a file, and we'll put it on the desktop. We'll use an AVI file. That's probably fine. We're actually extending the number of types of files we allow you to look at, but we'll look at all frames here, and that should be fine. Let's put it out on the desktop. We'll call this test 1. So what we're going to do now is we're going to generate all the different, so we've got 5, it's 150 frames. We're doing, most of the rendering, as you can see, is done off screen, which is great. There's two things about that. One, we're not limited to screen resolution when we do this, so if you want to look at a high resolution animation. The other thing is that it's a lot faster, not having to render this.
Yeah, oh, sure. And yeah, it's faster, and it, I think, though, the resolution issue is a big one. It allows you more control over it. You don't have to tweak the frame size or your window size for your application.
It looks like it's just about finished. So we have one additional thing we want to do with this, which is to bring it back into PowerPoint, and we wanted to make sure that we allowed for plenty of time for questions, and since we're at 48 minutes in, I'm going to go ahead and finish this up, put it into PowerPoint, and I'd like to turn it over. So if you have questions that you'd like to ask in regards to the quantitative analysis that we've discussed, or the qualitative analysis for comparing solutions, both test and or simulation, you can do one of two things. If you have microphone access, you can in fact raise your hand. I can unmute you and you can ask the question live, and we can have a discussion. Or if you feel more comfortable, you can just type into the questions tab, questions window, and we'll go over those questions as well. So, all right, just to finish up, so we're back in PowerPoint, and we'll drop in a new slide, and we'll grab that video file, which I'm assuming was out on the desktop.
Mm-hmm.
And I think we called it this one. Insert that. Takes a second to load. I don't know how big the file was, frankly, so. And let's just jump into Tecplot now, or into PowerPoint, and we'll take a second for PowerPoint, but you can see now that I can walk through that animation. And one of the cool things about PowerPoint 2010 is it allows you to actually go in and walk back and forth in the animation. So you can see that if you were presenting this, you can say, hey, 3/4 of the year you're going to see ingestion, so might I recommend you just move the intake port for the HVAC system to the other side of the building? You'd be better off.
Mm-hmm. Now we do have a question.
And we should have just views. So just a quick summary before we jump into the questions. We've talked about some strategies for comparing data from multiple sources. That's text data or Excel data. We've highlighted a couple of strategies for comparing qualitative and quantitative analysis of simulation. And we've talked about how you can kind of bring that into PowerPoint for your final report. At this point, we wanted to open it up to questions, and we have a few queued up here. Okay, let's see here. Plotting contours of multiple data sets in a single plot for comparison, and how would you do that? Like the example for string traces.
Well, certainly you can do, if you have multiple data sets in a single plot. There's a couple ways. I mean, you can read multiple data sets into a single data set if they're consistent, if they have consistent data structures. Same variables, same, mainly same variables. And then they just become other zones within the same data set, and you can, use, you can do plots on multiple zones with no problem. Now the second case is you have different variable sets. Say one is from an experiment, and one is from a simulation, and then you can actually overlay the two windows, make one window transparent, and at least if it's two-dimensional, then you can easily do you can easily see both plots simultaneously.
Okay. So that there was a significant number of people want to know, hey, how on earth did you get that Excel widget thing? And where do I get it? So I guess since that's a hot topic, let me just walk you through that quickly. Feel free to walk into. So I don't know what version of Excel you're using, but if you use Excel 2010, 2007, or 2003 was the last one, or was it 2005? They all have the same area, which is under Excel options. If you go into add-ins, then you just go to your manage the add-ins, and it allows you to browse. The add-in for Tecplot is usually in whatever directory you use to install Tecplot, which in my case is under Tecplot, and then 360 2010. And there's actually some utilities. And under the utility it says Excel, and there's a run Tecplot 5 XLA. So it's an add-in. So I'm not going to reload it. It would cause problems. Let's see. How do we compare visual numerical simulation solutions with data which are stochastic in nature, for example, environmental data where interpolation is not feasible and data is limited?
Oh, well, so you have stochastic data. I mean, that's actually a good question. I think in the end, you probably want to do some sort of averaging, an ensemble average, or say of your stochastic data before you try to do the comparison. And you can do averaging of multiple zones within Tecplot, provided the points are consistent. That would be my first recommendation. Now, I'm not sure if that's exactly what you were asking for, but hopefully that answered the question.
Yeah, another question came in around mapping from mesh to mesh. Let me go back to Tecplot here very quickly. We had talked about that data alter, where we specified an equation. We made a new variable called delta. And there really isn't much difference between what I showed you in the simple example using the test data and that from looking at data like these data here. So it looks like for a particular solution, I can make a delta and bring those data along, the same kind of thing here. And you can actually go from zone to zone. So it isn't much different. The other mechanism, if your data aren't grid point by grid point analogous, then you have to use interpolation. So you'd have to bring in both grids, and you'd have to do an interpolation between them.
And you can do interpolation in 3 dimensions as well. It works fine.
Mm-hmm. Jim Wong has a question. Jim, I'll ask you if you can go ahead and ask your question. Okay. See, we have another question from Jose. Jose, if you want to ask. Okay, well, it looks like perhaps the unmuting is not the best way. We still have a couple here. There was a question about what's new in Tecplot in terms of data size limitations.
Sure. Data size is, well, basically you can have, in terms of hard limits, you can have up to 2 billion data points per zone. Now, practically speaking, that would require a large computer with a lot of memory. Other than that, I'm not aware of any other hard limitations at this point to, well, it would also be 2 billion elements as well. So I'm not aware of any other hard limitations at this point.
Okay. There was a question about session availability, whether or not This would be available. Yes, the recording will be available, and we'll see about making some data that you could use in a similar way available in the same link so that you could walk through a couple of examples like this. Jose has a question. Let's see here. Go ahead and unmute. Jose, if you have a question, feel free to ask at this time. You can. You are unmuted, so if you want to ask verbally, you can do that as well. Okay, it seems like we're... Okay. Let's see, we're running close on time. Just a few more questions.
Yeah, the unmuting does not seem to be working, so...
not the way we intended.
Yeah, go ahead and type them in. That seems to be the best way.
Let's see, Muller had a question in your flow between the two buildings. Let's say you'd like to compare velocity magnitude behind the first building on the exact rate of points for comparison. Again, you can use the same extraction.
Right, you can do, well, you could certainly create a zone and you could interpolate to it from both of the zones that you're trying to compare. That would be one way to do it. In that case, it'd be a straight interpolation. We do have an exact point extraction capability. I think that might be what you're asking about. It is, I believe it's under the data menu. So there is a way to do it. In that case, it would be equal spacing points.
The last thing, someone, or maybe this we'll take this as the last question. There's a question about the tiling frames capability that I've shown here. Two things to point out. This will be available in the next version of Tecplot, but if you want to get your hands on it earlier, if you could send an email to us at either support.tecplot.com or you can send it to customercare@tecplot.com and we can send it out to you if you'd like to test it. Okay, well, looks like we're just out of time. I want to thank everyone and thank Scott for joining me this morning.
Well, thank you, Durrell, and I'd like to thank everyone as well. I think it was, I hope we helped you improve your analysis.
Thank you again, and this concludes our webinar on strategies for comparative analysis, both quantitative and qualitative. Thank you.